In this video, I'm going to be giving you an overview of what we're going to be doing in Chapter 4, and I'm going to suggest that you start off by watching the linear algebra review videos that I have, because I'm not going to be going over um, eigenvalues and eigenvectors and things like that, but I will be talking about them in this video. But this is just a big general overview of what we're going to be doing in Chapter 4 and what kind of applications we're working towards. So this first one, I wrote out our sort of lake diagram. I know I gave you a homework problem where we looked at two lakes or two tanks with salt in them. And in this case, what we could do, since these lakes or these tanks were in series, that is, there's one after another, we could say that Q1 prime, that's going to depend on the variables Q1 and T. So those were the input variables for our functions. And then Q2 prime was going to depend on Q2 and T, and also in some sense Q1, since it was determined by how much was in this, how much salt was in this tank here. But since we would solve for Q1, and here really, when we set up the two variables, the only ones we had to look out for were Q2 and T. We were able to just write out this entire equation in just terms of Q1 and T for this one and Q2 and T. The chapter 4 example is we have two tanks in parallel, and now these two systems are interacting with each other at the same time. So we're not going to be able to just solve for the first tank and then use that information to solve for the second one, because we have information, or salt in this case, going both directions on here. So Q1 says Q1 prime, rather, that's going to depend on, in this case, Q1 and Q2. And T, and so is this one, right? It's getting information from Q1, Q2, and T. So what that means is we're going to have to solve for these two tanks simultaneously. We can't just solve for one and then solve for the other like we did up here. We need to solve it as a system all at once. So I'll show you what that system might look like, and then we'll see how it relates to what we did in the linear algebra review. So if I'm going to set up a system of equations for this one, I'll say that what's happening in the first tank is, and I'm going to give these some sort of strange names, but you'll see why. So this is going to be some function times Q1 plus some other function times Q2. And then if we have some kind of inflow rate, something going on here, then we can also say that there's maybe some kind of function of t on there. So we'll call that G1 of t, since we'll have one for Q2 as well. Q2 prime is going to look very similar. So here we have some other function of t times Q1 plus some other function of t times Q2 plus G2 of t. And together, what this forms is what I'll call a system of, so we can think about what order this differential equation is, and according to your definition, first order says we look at this highest level derivative in here, and the rest of the equation can be put in terms of this highest derivative. So this is a first order We also, in this case, I'm assuming that it's linear, that I don't have any squared or sine of Q2 terms in here. So this is also going to be linear. And I'll leave it at that, differential equations. So I have this form. It's a system of first order linear differential equations. And I can rewrite this in another form. So I have a system here, but one of the skills that you need to have is to be comfortable to work in between these two forms. So the other form I'm going to have for this, I'm going to call this matrix slash a vector form, where we put everything in terms of matrices and vectors. So this first one here, according to the notation that we've seen, we can call this, well, maybe I'll write it. I'll write it explicitly this time. I think it's good to see it. So we have Q1 prime and 2Q prime is equal to, and if you think about how the matrix multiplication for this works, we have Q1 and Q1, Q2 and Q2. I'm actually going to leave this matrix on this, or sorry, this vector on the side here, and just concentrate on this. So if I think about the matrix multiplication here, if I kind of turn these variables sideways, I've got my two variables, Q1 and Q2. And the things I'm multiplying them by are these P11, P12, P21, P22. So if they're in this form like this, where you have, you always keep this consistent order, Q1, Q2, and then this term without any Q term in there. As long as you keep this nice form here, you'll end up with something that looks like a matrix with everything in the right spot, times a vector, plus another vector. So you may think that when you see this form that it doesn't look any nicer than what we were looking at up here. But the benefit of this is we have names for all these. We have conventions that we use for all these names. So this vector here, we could consider this just a Q prime vector. This matrix here, we could just call capital P of T. So I'll put everything underneath where it occurs in the problem. So this is the matrix P of T. We can call this, let's see, the Q vector. And then we'll call this one the G vector. Suppose I'll add a T there. So this is really nice because we've got a very condensed form of something that we have seen something that looks similar. So I'll compare this to what we saw in chapter 2 in a second here. But I just want you to be comfortable with this form. These Q's here are for when we're talking about salt. In order to connect it to what we're going to be doing before we get to talking about salt in tanks and these systems is I'll show you kind of the general form that we'll see. So all I'm doing here is just replacing Q with Y so that you can see what form we'll be looking at normally. In this form, what we have, this G of T vector makes this a non-homogeneous system. So if we wanted the homogeneous version of that, exactly the same as chapter 2, we'll just be looking at when g of t is equal to the 0 vector, so we can just not include it. So this is our homogeneous system. And this is the case where our g of t vector is equal to the 0 vector. Okay, when we start this chapter for the next 3 sections, we're just going to be looking at differential equation systems that look like this. Right? What I'll be doing is giving you some kind of system of differential equations, and you'll be solving it for this. I'll do an example of that based on the example that you saw in the linear algebra review, so you can see how this all connects. But the basic breakdown of, well, I'll start the problem and then I'll describe what we do. So here's the problem. Let's say I want you to find the general solution for the following system. So the system I'm going to look at looks like this. So this is a homogeneous system because we don't have any t terms hanging out on the side there. We'll save that for, I believe, section 4.7. So when we start talking about that. But if we're looking for the general solution to this system, this is where I want to kind of tell you what we're going to be doing before we do it, because we follow the kind of same procedures. Excuse me. We follow the same procedures for solving these, and there's quite a few steps. So if it's in this form, we'll call this the system form. The first thing we want to do is convert it into we want to convert it into matrix and vector form. So we have the system form. I want to convert that into matrix vector form. And so we'll do that. Say this is the same as, this is the same as my y prime vector. Here, I'm going to show a couple of unnecessary steps just for clarity in these first couple examples. So thinking about our matrix multiplication here, the matrix, if we want to say 1, 2, 2, 1, that's going to be multiplied by y1 for this column and y2 for this column. So y1, y2. Okay. Now we can take this and we see that this is the y prime vector. And there we go. When you get to doing the homework, you might even see some problems so they'll be bolded. Again, remember that what I'm drawing is vectors here, just going to look like bolded letters. But when you're asked to solve a system of differential equations, you might just get this. So you're going to have y prime vector is equal to some 2 by 2 matrix times the y vector. And once you do this, sometimes your book calls this P, sometimes your book calls this A, and I think that mostly depends on whether or not there's functions in here or if there's just numbers, just constants in here. But this is our sort of constant coefficient first order linear system of differential equations. But we're going to take this matrix, and the first thing we'll do is find the eigenvalues. And then we're going to find the eigenvectors. And then we're going to write the general solution. So we saw from last time so from our previous work, we saw that our eigenvalues were that lambda 1 is equal to 3, and lambda 2 was equal to -1, and then the corresponding eigenvectors that we found. This is going to be 1, 1, and that the second eigenvector was equal to 1, -1. So again, we did that in previous videos. We worked with this matrix here, right, finding those eigenvalues and eigenvectors. And once we found those, what I mentioned briefly in the previous video was that once we have the eigenvalues and the eigenvectors, is that we can write the general solution here. So in this case, the general solution, which is going to look like y vector, is going to be c1 y1 vector plus c2 y2 vector. So very familiar from what we saw in chapter 2. This time we're just looking at vector solutions instead of just single formula solutions. Now y1, if I can replace that, y1 is going to be e to the lambda 1t times the first eigenvector, and y2 is going to be replaced by e to the lambda 2t times the second eigenvector. I wrote this form out here because this one will always be true. So this form this will always be true. We can always write it like this. But I'll say that this form isn't always going to work. But what I will say is this form is specific to when we have two real eigenvalues. Right. So just like in the third chapter when we had different things that we had to do, or different forms for our general solution depending on whether lambda was repeated or maybe lambda was going to be a complex number. So we'll see the same thing. This is sort of the basic form when we have two real eigenvalues. And then in the next couple sections, we'll look at what happens when lambda is repeated or when lambda is going to be, when lambda is complex. But this is the two real eigenvalues, two different, let's be specific here, two real distinct eigenvalues. Okay, stop delaying actually writing out the final answer for this. So this is going to be e to the 3t times 1, 1 plus c2 times e to the negative t times 1, negative 1. Something else to notice here. Here, draw a little box around here because we're pretty much done. If all I ask you to do is write the general solution for this, this is a perfectly acceptable answer. And something that I'll note here is that if you remember when we chose the value for this particular eigenvalue, this eigenvector element, we chose 1 here, but we could have chosen, let's say, 2. In that case, that's taken care of by this C2 here. So C2 would just be half of what it was in this example. Or if we chose negative 1, this eigenvector might be negative 1 and 1, but this C2 takes care of that. So when we're writing this general solution, again, we're sort of accounting for we can choose any value we want if we have that degree of freedom. It also lets us have lots of different eigenvalues and different eigenvectors. Eigenvalues should always be the same. Okay, we can do a little bit of matrix algebra. So I'll say this is our general solution. So there's our general solution. I'm going to do just a little bit of some matrix algebra to rewrite this a little bit and see if we can have some fun with this. So this is, again, still our general solution. Right. So this is C1 times e to the 3t, e to the 3t, plus C2 times e to the negative t, negative e to the negative t. Another interesting thing we can do with this is we can rewrite this as a matrix of our solutions times a constant vector. So this is, excuse me, so this is going to be the matrix e to the 3t, e to the 3t, times e to the negative t, sorry, not times, just different variable here. So you can maybe spend a little bit of time convincing yourself that, let's see, e to the 3t times c1 plus e to the negative t times c2. Okay, that all checks out. Just making sure that these two things are equivalent to each other. The reason I wanted to show you this is your book has a special name for this matrix here, and sometimes it's really nice to have this just compact matrix as a solution, because we know that we're always going to be doing C1 times this, C2 times this. So the name that we give this is a Greek letter, and I'm currently blanking on what Greek letter this is. I think it's, I don't know. I'll be sure to look that up. Sorry about that. Anyway, this is some constant vector, so a vector of all of our constants. But this thing here, this is our solution matrix. So you may be asked to give your answer in the form of a solution matrix, but if you want to look at sort of our version of the general solution that we decided we were done with, and it's really not that difficult to convert between these two forms. If you have this, you're really just multiplying your solution by your eigenvectors, and then you can kind of smush them together. So a little bit more mathematically rigorous to say smushing together. And this is maybe a little confusing when you see this in your book, but the solution matrix is equal to a so this is not a plus, this is not a set. This is kind of a weird notation here. So this is a vector of vectors. Right? So when we make this matrix here, you can see that this piece here is e to the 3t times 1, 1. So that's our first solution there. And then the second column there represents e to the negative t times the eigenvector 1, negative 1. So in summary, we can say that this solution matrix is, say this uses the columns, sorry, uses the solutions y1, y2 as columns in a vector. Okay, I think I need to end this video before I make too many more mistakes in what I say, but everything I wrote down is true, hopefully, but I will see you in the next video.